Hey everyone, and welcome to this explainer. Today, we are decoding a really fascinating academic roadmap that lays out the core architecture behind our digital security. We're going to dive into the foundational source material for algebraic structures and coding theory and unpack exactly how the dense theory you see on a page actually translates into the secure systems we rely on every single day. So you might be wondering, how on earth do abstract algebraic structures actually solve real-world security problems? I know, it sounds like a massive leap to go from high-level theoretical math to the tools keeping the internet safe. But, as we're about to see, the two are completely inseparable. To figure that out, we're going to follow this syllabus from the top down. We have 1. Designing real-life solutions, 2. Core algebraic structures, 3. Mapping mathematical relationships, 4. Essential self-learning topics, and 5. Cryptography and network security. All right, let's kick things off with Section 1, Designing Real-Life Solutions, or the Ultimate Objective. This is the crucial starting point, the whole reason we're doing this. The ultimate goal is applying these abstract concepts to design communication systems that are secure, reliable, and socially responsible. You're not just memorizing math to pass a test, you are literally learning how to build frameworks that actively protect society. Moving right along, we enter Section 2, Core Algebraic Structures, which are basically the building blocks. Taking a step back to look at the foundational components, everything starts with one defining rule. We are exploring algebraic structures built around a single binary operation. This is the absolute bedrock. Everything else we talk about grows directly from this one concept. From that starting point, you sequentially build up your toolkit, getting a little more complex at each step. You start with semigroups, then you step up to monoids and standard groups, and finally, you reach the abelian group. The initial goal here is just to successfully identify every single one of these structures based entirely on their specific binary operations. But wait, the toolbox doesn't end there. To really round out these core capabilities, you also have to master cyclic groups, identify normal subgroups, and get a really solid grasp on codes and group codes. Think of these as the intricate little gears that allow the whole mathematical machine to function out in the real world. Let's move to our next section to see how this builds, focusing on how these individual structural blocks actually relate to one another. This is Section 3, Mapping Mathematical Relationships. This is where we see a really cool shift in complexity. Early on, the task is simply identifying base structures, spotting a semigroup or a monoid. But as we advance, the challenge evolves into identifying relationships. You're figuring out if these structures mirror each other through isomorphic or homomorphic connections. It's like going from just staring at isolated Lego bricks to analyzing exactly how they map onto one another. And this structured mapping shows exactly how those learning outcomes are strictly tied to specific academic performance indicators to maintain some really rigorous standards. Notice how the later outcomes demand a much higher standard, hitting multiple indicators at once? That's because they require you to actively analyze and design rather than just identify what's in front of you. Now, as a digital architect, your journey also involves an independent quest, which brings us to Section 4, Essential Self-Learning Topics. You won't be handheld through every single concept here. A vital part of this roadmap means you have to independently tackle some specific advanced topics on your own, namely cosets, Lagrange's theorem, and the product and quotient of algebraic structures. Cracking these independently is absolutely critical to completing your mastery of the framework. And finally, we reach the climax of the course contents with Section 5, Cryptography and Network Security. This is the real-world application. Cryptography. This right here is the ultimate payoff for all that math we've explored. It is time to take those algebraic structures and analyze them to solve actual pressing problems in network security. We are literally relying on them to lock down, secure, and encrypt vital information flowing across global networks. Plus, it isn't just about keeping data a secret, it's about keeping it accurate too. You'll use these exact same concepts to ensure data integrity through highly sophisticated error detection and error correction. When digital signals get crossed or a bit flips during transmission, it's this exact mathematical architecture that instantly catches the mistake and fixes it. The scope expands even further from there. It turns out these single binary operations actually lay the crucial groundwork for automata theory, which explores exactly how machines process logic and perform incredibly complex computations. And in tandem with that, it explicitly ties all of this algebra directly into the creation and understanding of formal languages.
Seriously, by the end of this roadmap, you'll see how these algebraic structures are essentially the core grammar and syntax that define computer science itself.
So, as we wrap up this explainer, I want to leave you with this final, empowering challenge drawn straight from the course outcomes to kickstart your own journey into digital architecture. How will you apply these concepts to design secure, socially responsible communication systems? The blueprint is right here in front of you. Now, it's time to build.